Hello, this video is for Stat 110, Module 2, Part 1, and includes a discussion of the elements of hypothesis testing. In Module 1, we considered a variety of investigations. In some of those investigations, we were interested in the left side of the reference distribution. Other times we were interested in the right side. We introduced the idea of a reference distribution, the idea of a outlier rule, or 5% outlier rule. All of those are various elements of hypothesis testing. And here what we're going to do is bring those elements together and just kind of talk about those in a more cohesive way. So that's what this first part is in Module 2, is just to go back through what we have been doing and putting more structure around the investigation and how we do the investigations. And this structure is called hypothesis testing. Okay, let's go ahead and get started then with our handout. So the first thing that we're going to need to worry about is the writing of the research question. This is done oftentimes by the researcher and without the statistician's help. So oftentimes in practice, a researcher will develop a research question and collect data, and then after they have the data, will come and see us as statisticians with the help, and we help them with their analysis and answering their research question. So this is the first step that needs to be done before we can do an investigation. We have 3 case studies that I'm going to look at throughout this handout. We have the gender discrimination case study, which we looked at in Module 1, and that was asking whether or not there was evidence of gender discrimination against females in the hiring of faculty at the University of Texas at Dallas. We had a staring example, and that research question: is there evidence to say the woman in the study had the ability to correctly identify when somebody was staring at her? And then also we had the ear infection example, and we were just interested in whether or not there was a difference in the duration of fluid in the middle ear between breastfeeding and bottle feeding in babies. So again, that's the first step in developing or doing a hypothesis test, is understanding what the research question is. And as I said, oftentimes these are written by the researchers and the statistician is not involved in that process. Okay, let's talk about a couple of concepts that are going to be important as we move forward. And the first is the scope of inference. So the scope of inference is defined to be to whom the study outcomes or conclusions apply to. The parameter is the numerical value that is going to be tested in our investigation or in our hypothesis test. And oftentimes we denote that parameter with a Greek letter pi. Or the simulation app identifies that quantity as the p value. So let's talk about the scope of inference for our 3 examples. So the scope of inference for the gender discrimination case is going to be the women who were seeking a faculty position within that particular division at that particular college. So it's not just the people that were actually hired, but we were trying to evaluate discrimination. So it's going to be the people that were hired and the women that were not hired as well. The parameter for that situation is the probability of a female being hired under a situation of no discrimination. And from the data, we determined that that value was 38.3%. The parameter is how the reference distribution is set up. So let's do another example, the staring example. The staring example just had one particular woman that was being asked to participate in that staring exercise, being able to identify whether or not the individual was staring at her or not. So the scope of inference there is just that one particular woman in the video. The parameter there is going to be the probability that this woman in the study could correctly identify being stared at under a situation of no ability again. So the parameter value for that situation is going to be 50%. Let's talk about the scope of inference for the ear infection example. So the scope of inference are, again, not just the individuals that participated in the study, but the individuals that they would like to make conclusions about. So this is going to be babies that were either breastfed or bottle fed. Now, it is difficult to determine exactly which babies would be considered within the scope of inference, because we don't have information about how the researchers identified these babies to be used in this study. So babies from a particular medical clinic maybe were used, or maybe from a particular geographic region. So if they used babies at a particular medical clinic, let's say in the Twin Cities, then I don't know if the scope of inference would include babies, say, from India. So the healthcare system and the beliefs about breastfeeding or bottle feeding might be different in India. So babies from India probably are not in my scope of inference. So oftentimes it's difficult to determine exactly who is in the scope of inference for a study, especially if the authors don't give us a lot of information about how they picked the individuals to be in their study. Okay, let's talk about the hypothesis that actually get stated when we do our investigations. We have two of those. We have the null hypothesis and we have the alternative hypothesis. The null hypothesis is how the reference distribution is set up. So that determines how the reference distribution is going to be set up. That's called the null hypothesis. The alternative hypothesis, then, is just a restatement of our research question. It's an endorsement or a confirmation of the research question. Now, these null and alternative hypotheses usually include the parameter value that we are interested in testing our data against. So let's look at the following table here. Let's do the gender discrimination one here. The research question was, is there evidence to suggest gender discrimination against females in the hiring of faculty at the University of Texas at Dallas and within that particular division, humanities and arts? So the research question gets put into the alternative hypothesis. So the alternative hypothesis here is that there was bias against females, and the probability a female is hired is actually less than that 38.3%. So again, the alternative hypothesis here would support the research question, or is a confirmation of the research question. The null hypothesis is how the reference distribution is going to be built. And that's going to be built under the situation of no discrimination. So the null hypothesis is going to read here, the hiring is fair, and that the probability of a female being selected is that 38.3%. Now, we statisticians usually write our null and alternative hypothesis as given on the right-hand side of this table. So again, this pi here is just for the parameter value. And here I'm specifying that the pi is equal to 38.3%. In the alternative, I'm going to say that the chance or the probability of a female being hired is less than that fair rate of 38.3%. Is less than that 38.3%. Okay, let's do the ear infection example here. So the ear infection is there evidence to say that there is a difference in the duration of fluid in the middle ear between the breastfed and bottle-fed babies. The researchers were hoping to show that there was a difference between those. So that's what goes in the alternative hypothesis. Again, the research question gets put into the alternative. So here we're going to have that the parameter value is different than a 50-50 situation. The null hypothesis is going to be the situation of no difference. So that is going to have the probability of breastfeeding baby doing better than a bottle-feeding baby is going to be equal to each other. So those two probabilities are going to be equal to 50% here. So we set up that reference distribution under a 50-50 scenario. Okay, this table here just shows you that indeed the null hypothesis value is what gets put into the app when we're building our reference distributions. So whatever is in the null hypothesis here, for the gender discrimination, that's going to be equal to 38.3%. We put that in the app as shown. Now it needs to go in the app as a decimal value. So I need to move that decimal over 2 places to the left. For the staring example, that was a 50-50 scenario. The two outcomes were either she was correct or incorrect. And here we're putting the parameter value of 50% or 0.50. Likewise for the ear infection example. Now some people write the null hypothesis as everything not contained in the alternative. So the way that I've been doing it is just writing that the parameter value is equal to 38.3%. That's what I have down here. That's how I typically write it. But some people are going to write it like I have over here on the right side. Notice that the alternative is exactly the same. But the null here, I have it set equal to 38.3%. Other people might write it as bigger than or equal to 38.3%. Even when we write it like this alternative specification here, we construct the reference distribution at the equal, or what we call the least desirable position. And that's going to be at the equal. So as close as possible to the alternative, but not in the alternative. So when we construct the reference distributions, we simply use what that value is equal to in the null hypothesis. Okay, one other quick thing that I should probably mention here is that there's some types of situations that we cannot evaluate with a reference distribution or with the process that we have described. So here I have version A. This is, it looks like it's the two-tailed example. So is there evidence to say a difference exists in the duration of fluid in the middle ear between breastfed and bottle-fed babies? That's the example that or the one stated above. This is how that would be set up, and this test is possible. Version B is not possible. So all I've done here is there evidence to say that there's no difference in the duration of fluid. Okay, so that slight change of wording there cannot be done with our standard procedures. If we did a no difference, okay, then this is what the null and alternative hypothesis would look like. And this isn't possible because I don't have one particular value that I can use to set up my reference distribution. So under this situation right here, I have many, many possible choices to use in choosing my reference distribution. So for example, I could use 55% to build my reference distribution, because that would be a value under the null. I could choose 83% to use to build my reference distribution, because that would be another value under the null. I could use 62.35% because that would be another value under the null. So again, the reference distributions are built under the null hypothesis. But in the one that I have here, there are many, many different values that we could use to build the reference distribution. And certainly, what we determine an outlier to be in this reference distribution is going to be different than this reference distribution and is going to be different in this reference distribution. So we don't have a single particular value that we can use to build our reference distribution. And for that reason, this type of research question cannot be evaluated through the use of a hypothesis test. Okay, so we've already used the term reference distribution. Now it's clearly defined here for you. It's just a graph that is used to measure and evaluate the amount of evidence data has for a particular research question. These reference distributions, again, are obtained using the simulation app that we've already been using. So when I obtain many repeated outcomes, okay, I am building a reference distribution. Here's what those would look like for each of the 3 case studies under consideration here. Okay, so making a formal decision, we're going to do that with the outlier rule. We've already been doing that. We're going to use the 5% outlier rule because that's what we use in determining statistical significance. So one of our founding fathers of statistics, modern day statistics, R.A. Fisher, he made a statement that 1 in 20, okay, should be used in determining statistical significance. And since that time, which was almost 100 years ago, all statisticians, and actually all people, not just statisticians, when they're trying to determine statistical significance, it is assumed that you are using the 1 out of 20 rule, or the 5% rule. 1 out of 20 is 5%. So that 5% outlier rule is used almost entirely, not just within statistics, but everywhere. So when I help people with their analyses in social work, if I have a faculty member in social work that needs some help, she knows about the 5% rule, and that's what we're going to use. If I have somebody else in business school, they're going to use the 5% rule in evaluating their evidence. If I have somebody in biology, they're going to use the 5% rule in evaluating their evidence. So that rule is very much ingrained in the process of establishing statistical significance. Now, in the gender discrimination case, we were worried about the left side of the distribution because that was evidence of discrimination against females. So the outlier rule sat on the bottom 5%. We used the bottom 5% in determining the outlier rule for that particular example. In the staring example, okay, evidence of an ability would mean that she would be getting more correct than we thought under a guessing scenario. So here we would put the 5% on the right side. And in some situations, we put the 5% on both sides. We put 2.5% on the upper side, 2.5% on the lower side, and we're going to have a lower cutoff and an upper cutoff for the two-sided examples. And that's the only 3 types of tests that we have: left-tailed, right-tailed, and two-tailed. And when we were using the simulation app, those were the only 3 buttons that we used or had there to determine the outlier rules. Making our formal decision, if the outcome falls in that bottom 5% or that top 5%, or in the two-tailed example, the outside 5%, then we can say that we have enough evidence or statistical evidence for the research question. Or we say that the data provides enough evidence for the research question. Now, if it does not sit in the bottom 5%, top 5%, or outside 5%, then that means it's too close to the middle. And the middle of that reference distribution is usually set up under the fair or no difference scenario. So that's not going to provide support for your research question. So let's look at a couple examples here with the outlier rule. This is the gender discrimination example. There was, I think it was 49 women that were evaluated there, or 49 people that were evaluated. I think 14 females were hired. It should have been around, it looks like 18, I think. The bottom 5%, I believe, that we obtained was 12 or lower. So this outcome from my study does not sit in that bottom 5%. So in the gender discrimination example, we did not have enough evidence for the research question. We did not have enough evidence to say that discrimination was taking place. It was kind of close, but it's not within that region. Another way to think of that is for this reference distribution was obtained under a situation of fair hiring, and 14 kind of sits within the realm of the fair hiring there. It's not enough of an outlier to be deemed statistically unusual. On the other hand, when we looked at the parole discrimination case study, the Native Americans paroled was indeed in the bottom 5%. So 24 here sits down in the bottom 5%. I think the cutoff here was 28. So 24 does indeed sit in that bottom 5%, which would be unusual or atypical if the paroling was done fairly. Well, in both of those cases, in the gender discrimination case, we did not have enough evidence for the research question because the study outcome did not fall in that bottom 5%. However, in the Native American paroled example, we do have enough statistical evidence to say that seeing 24 is unusual or is an outlier. We do have enough evidence to say that discrimination was likely taking place against Native Americans being paroled in Nebraska during the time of that study. Again, because 24 does fall in that bottom 5%. Now, that approach there requires us that we identify what the value is in the reference distribution to be unlikely. And we can circumvent that step or make that step a little bit shorter by using what is called the p-value. So the p-value, what is the p-value? It is simply the probability of observing an outcome as extreme or more extreme than the outcome from our study. This p here stands for probability. Okay, so this is a value that is always going to be between 0 and 1. And when I mention or when we say as extreme or more extreme, this includes the outcomes that would provide as much or even more support for the research question. Okay, so when we say as extreme or more extreme, we are talking about values that would support the research question. So again, let's look at the staring example. The staring example was set up with a number of trials between 0 and 20. The parameter value was 50%. Again, that's where the expected value is going to be here. You would just multiply 20 times 0.5. It's going to be 10 here. The actual number of the actual number of correct that the woman in the video got was 14. So that's there. And this is a right-tailed test because the research question asked about her ability to identify when somebody's staring at her. So the research question here is stated up above. Is there evidence to say that this woman has the ability? Well, if she has the ability, then she should be getting many, many correct. So the right-hand side of this distribution is going to be used in computing the p-value. The p-value is going to use values as extreme or more extreme than the study outcome that provide even more support for the research question. So to compute the p-value, what we're going to need to do is to figure out how likely is it that this woman would get a 14 correct, 15 correct, 16 correct, 17, 18, 19, or 20 correct. So we go from this point right here and all the way to the right. Now this is different than trying to determine what the 5% outlier rule is. Because the 5% outlier rule, what we do is we try to find that top 5%. We try to find a cutoff value for that top 5%. Now that is different than the p-value. What the p-value does is we start here, we start at the outcome, and we find the probability of that outcome plus anything greater than that outcome. At least we do it that way for a right-tailed test. If we were doing a left-tailed test, we'd be down here and we'd be doing this particular, wherever the study outcome was, and anything to the left. So what outcomes from this reference distribution would be considered as extreme or more extreme? As I just stated, values 14 through 20. To compute the p-value, what I need is just to figure out how many of the dots from my reference distribution were at 14 or anything higher than 14. I'm not going to count them here, but I guess there was 15 dots. I put 200 repeated outcomes on this reference distribution. So 15 divided by 200 is going to be 7.5%. So there's a 7.5% chance of seeing 14 or anything higher than 14 when this woman is guessing. Okay, because this reference distribution was built under a situation, well, if we go back up and look, it was built under a 50-50 situation. Where was my parameters at? It was built under a 50-50 scenario. So the reference distribution is built again, assuming she did not have the ability. So the chance that a woman will get 14 or more correct under a situation of no ability is 7.5%. Essentially what that tells me is 14 sits in the top 7.5%. It does not sit in the top 5%. It sits in the top 7.5%. So 14 would not be considered a statistical outlier here. It's not extreme enough. So 14 would not provide evidence for the research question. Okay, some general comments about p-values. I will let you just read those if you want. I will skip over those. How to make a formal decision with a p-value? Well, if the p-value is less than 5%, then the data, if the p-value is less than 5%, then we can say that the data provides enough statistical evidence for the research question. If the p-value is not less than 5%, then we must conclude that the data does not provide enough statistical evidence for the research question. And we use that 5% threshold as a very strict rule. If we're below that 5% threshold, we do have enough evidence for the research question. If we're not below that 5% threshold, then we lack evidence for the research question. Here's a little bit about, well, can't we have strong evidence and marginal evidence and no evidence or lack of evidence? Okay, we try to stay away from terms like marginal evidence here. Essentially what was said here is that we would just start arguing over where the limit should be for marginal evidence. So what we've done here is we made a pretty strict rule of that 5%. If you're below that 5% with the p-value, then you do have enough statistical evidence for the research question. Now if we go back up here and look at the staring case, 14 was not, the p-value here was 7.5%, which is not less than 5%. So 14 is not extreme enough. So I do not have evidence for my research question. 14 sits too far back into the reference distribution. Again, the reference distribution indicating no difference, or that she does not have the ability. So it sits too far back into this. If this p-value was 3%, then we're not going to have very many red dots out here, and that would be pretty extreme. And we would say that it does have enough evidence. So again, the rule is, if the p-value is less than 5%, then we have enough evidence for the research question. Example 2.1.4 here, real quickly, is just a two-sided example. So this is the ear infection example, and we need, when we're doing the p-value, we need both sides. So we did kind of go through that in one of our examples in Module 1, but I'll just be more careful here. So in computing the p-value, I'm going to need values that are as extreme or more extreme. That would provide evidence for the research question. So here that's going to be the values 16, 17, 18, 19, 20, 21, 22, 23. But because this is a two-sided analysis, I also need to worry about values that are extreme on the left side. So how do I figure out the values on the left side? Well, 16 here, let's go back up here and look. 16 here is 4.5 away from the middle of this curve, or this reference distribution. 16 is 4.5 away from the expected value. So I need to drop 4.5 down and use anything that's more extreme than that on the left side. So if I drop 4.5 down, I'm going to be at 7 here. So the p-value is also going to use probabilities or values that are 7, 6, 5, 4, 3, 2, 1, 0. So the p-value is going to use both 16 up through 23 for its calculation and also 7 through 0 for its calculation. So when computing the p-value, I'm going to need to worry about both sides. Here it looks like I used 100 repeated outcomes. I have 5 dots on the lower side, so that's going to be 5 out of 100. And I have 6 dots, it looks like, on the upper side, so I got 6 out of 100 for the upper side p-value. I put those two p-values together and I end up with a 11%. So the p-value for this problem would be 11%. Again, what that tells me is that 16 is not that extreme in this reference distribution. So I do not have enough evidence to suggest that breastfeeding or bottle feeding is any different from each other. Now it's close. Okay, it's 11%, but it's not less than that 5%. So here in this table, I'm just showing you our statistical decision. So the rule is going to be, is the p-value less than 5%? And it's not here. So I do not have enough evidence for the research question. Same thing for the ear infection example. Okay, we're just about done. This is a long video, but we're just about done there. So the outlier rule and the p-value rule are going to give me exactly the same value. So here, let's look at the Native American paroled. The study outcome was 24. 24 sat in the bottom 5%. So if I was using the cutoff approach, what I would do is trying to find the bottom 5% of the distribution. I would say that my outlier rule was the cutoff value, or the threshold value, was at 28. And 24 was below that 28, so it was definitely in the bottom 5%. Now if I use a p-value, what I can learn is, with the p-value, what I'm going to do is determine the values that are 24, 23, 22, 21, all the way down. So I know from a p-value that 24 sits in the bottom 0.3%. So I can compare 24 against 28. That would be using the 5% outlier rule. Or I could just compare this 0.3% to this 5%. That would be using the p-value approach. So those two are going to agree. What if my study outcome was at 26? Well, it's still in the bottom 5%, and the p-value there is going to be 1.2%. So again, the p-value is going to be using the probability that I got a 26, a 25, 24, 23, all the way down to 0. So 26 sits in the bottom 1.2%. So it certainly sits in the bottom 5%. So again, the outlier rule and the p-value rule are going to agree. So what if the study outcome is above? Well, if the study outcome here is not in the bottom 5%, so it's not below the 28, instead let us suppose that it's 30, then the chance that I'm going to get 30 or less is at 11.7%, I guess, from this reference distribution. So 30 is not less than 28. That would be using the outlier rule. If we use the p-value approach, 11.7% is not less than 5%. So you're going to be guaranteed to get exactly the same outcome from your test using the outlier rule or the p-value approach. Now in practice, we tend to use the p-value approach because I just need to compute one probability value and just compare it against 5%. And nowadays, we're able to get those probability values real easily from our technologies. Okay, the last component, writing the conclusion. So making a decision here. So what I've talked about here is we do not have enough evidence, or we do have enough evidence. That's what we call the decision about the test. The conclusion is something that should be written just in everyday language, or sometimes I'll say in layman's terms. There's three components that I'm going to be looking for when judging whether or not a conclusion is well written. It needs to identify whether or not the study supports the research question, so it has to include the decision. It should restate the original research question, so it should be very clear what was being tested. And then finally, it should communicate the amount of evidence that we have for that research question. Different measures of evidence are the p-value. We could also use the margin of error when we learn about that. There's another quantity called the effect size. You could use that as an acceptable measure of the amount of statistical evidence that we have. Now, the only one that we have at our disposal now at this point is p-value. So for now, we're going to be using p-value in our conclusion statements. So let's break out the three parts here for the parole example. We have the research question. We have the decision, which involves making a evaluation of our p-value against the 0.05 level. So here the p-value for the Native American discrimination case was 0.003. That's less than 0.05. Be careful there, don't use 0.5, but use 0.05. So we do have enough evidence for the research question. Now the conclusion is going to be in three parts, or I need three parts. And here I've just written it out so it's easy to see the three parts. The first part is the decision, so I do have enough evidence. The second part is just the research question. Again, asking about discrimination taking place against Native Americans by the state of Nebraska during this particular time period. So that's just a restate of the question. And then lastly, the amount of evidence that we have, which we can just express that with a p-value. I usually just put that in parentheses at the end of the statement. So here's a couple more cases or examples. The staring one, here we do not have enough evidence. So again, the p-value there is not less than 0.05. So that's just going to influence my decision here. There is not enough evidence to say that the woman in the study has the ability to correctly identify when someone is staring at her with a p-value here of 0.075. So I need, again, these three components when writing a conclusion, or that's what I'm going to use when determining whether a conclusion has been correctly written. Okay, that does it then for the elements of hypothesis testing. There were no questions in this, but I asked you just to check the box there at the bottom of the notes to ensure that you've watched this video. Okay, thank you very much. Have a good day.